So what I'd like to do today is sort of do a preview of homework set 9. So homework set 9 is really one of my favorite sets of homework because it involves a lot of problems that use some nice skill sets. It really pulls things together in the course. We bring in some molecular modeling and conformational analysis in some of the problems. And it sort of serves to epitomize all of the techniques we've talked about, and particularly that sort of problem-solving handout. These are all problems of my creation with TAs for the class, and they really represent, I think, some of the best of the best. They're all set up to be reasonably satisfying. You know, it's been sort of pick and choose among the best problems from final exams over the years, and I think they really illustrate some points. So what I'm hoping to do is give you some pointers on these problems to get you started, and really to sort of take you on a little bit of a guided tour of what you're going to see as you go along and work these problems, illustrating some of the techniques and tools that you're going to be using. At the end of today's session, or shortly thereafter, what I'll do is take all of the handouts that I've annotated during the course of this, and I'll email it off to you. So feel free to either take notes on the handout or treat this like a PowerPoint presentation, a slide presentation, where you know that you'll have the handouts at the end, whatever works best for you. So the homework problems run 1 through 5. The first problem features Toxie and Rosie. Normally I give my lecture on Toxie and Rosie a little bit later in the course, so it's more in sync with this homework set, but this is going to draw on some of the skill sets of this. This was a problem that was put together by a graduate student, Michael Chung, who was also a TA for the course, and this was from his research project. And it very nicely uses the skills of Toxie to assign a peptide, to assign a set of different isolated spin systems. And I just want to take you through one representative example and then show you what we're going to be looking for, sort of illustrate the NOEs that we might observe, the ones that we're going to think about and try to observe. So I had already talked a little bit about this problem before, and I'm just going to share my screen with you and walk you through one of the Toxie tracks here. All right, can you see my screen okay?
Yes.
So this is a molecule that contains a couple of aromatic rings plus a phenylalanine, and then several other amino acids, including valine and isoleucine. And Michael Chung found that it formed a hydrogen bonded dimer, and you could very easily see this in the Rosie spectrum. So I'm going to, oops, my iPad isn't. Okay, I'm going to take us through one of the Toxies and just remind us of how we go ahead and can get all of the resonances off of from cross peaks here. Basically, pick out an entire spin system as long as it's not too long. And the great thing about Toxie is, as long as you have one resonance that doesn't overlap, you can pick out all the cross peaks off of it, even if you have a region that's really quite a mess. So like this region over here is quite a mess. It would be pretty hard to cozy our way through it. But let me show you how nicely Toxie works. And I'll just pick this triplet here that's isolated. And we're going to figure out which residue this corresponds to. So I'm going to go ahead and I'm just going to draw a line through all of these cross peaks. This is one quadrant of the spectrum. So this is the region that's more upfield. So it's about from 1 to 6 ppm that we have here. And immediately when we notice a couple of these cross peaks, so I've numbered all the resonances, we notice a couple of these cross peaks. So for example, here we have a cross with resonance 40, let's see, this one is 46, and this is 45. And so immediately we notice on these resonances, we've got a methyl, 3 hydrogens, we've got a triplet and a doublet. So immediately we know that this is the isoleucine reference resonance. And I'm just going to remind us of what we have in the isoleucine. So we have the NH, we have an alpha proton. The alpha protons are reasonably downfield. The proton I picked for starters was at about 4.7 or 4.8 parts per million. So that's the alpha proton. We have beta protons. We have the gamma methyl group. That gamma methyl group is going to be split by the beta proton. We have gamma protons, gamma methylenes, and then we're going to have a delta methyl group, which is going to be split by the gamma methylene. So pretty obviously, if you look at this triplet methyl group here is going to be your delta methyl group, the one that's split by the methylenes. And this doublet here is going to be your gamma methyl group. And then you've got 3 more resonances. So this isn't, right, it's not a valine, right? If it were a valine, you'd just have 1 beta proton. So we've got 3 resonances here. These resonances are going to correspond to a cross peak with 44 rather, a cross peak with 40 right over here, and a cross peak with 38 in this mess right over here. And so collectively, these 3 resonances are going to be the rest of the betas and gammas. We may not be able to assign them, or maybe now we can use COSY to be able to assign them. And here, this resonance 24, which crosses, right, this is our diagonal over here. So this resonance 24 is the alpha of the isoleucine. And then if we continue on the next slide, so this was sort of one quadrant of the spectrum. If we continue on the next slide over here, I've just taken a different quadrant of the spectrum. And if we continue to trace off of resonance 24, now we find that we get a cross peak over here. And that cross peak here with 8, right, you can see it just right over here with 8. That's going to be our isoleucine NH. So the point is, in one relatively painless fell swoop, we've managed to assign the resonances of an entire amino acid. And you'll be able to work off of the other alpha protons or off of even the NH protons, which are over here, and track in one way or the other to pick up all of your different resonances and assign the various resonances. I pointed out before that on the aromatics, you see a 1,2 disubstituted aromatic and a 1,2,4 1,2,5 tri-substituted aromatic, and you'll be able to work your way around those and pick those out. So the last thing I'm asking you to do on this is to start to look for NOEs that might be evidence of dimerization. And this drawing is reasonably explicit in terms of hydrogens, and so you might start to surmise what might be close to what. And so even if you're not sure of it, you sort of will have a hypothesis that maybe this hydrogen and this methylamide NH, maybe the hydrogen at the 6th position of this aromatic ring might be close. So we might look for that NOE. We might expect to see this NOE as well. So again, I'm going to put question marks here. We might expect to see that NOE. We might expect to see this NOE. here. So I'll sort of put question marks for all the things we might look for to see if we might see those NOEs. And of course, the molecule is C2 symmetric. So basically, whether I do this on the left or the right is not going to matter. Here's the one we won't be able to see because these two protons are the same resonance. So you can't see an NOE be of a resonance with itself. So we won't be able to see that. And we can look in the ROSI for all of these NOEs. If you need help assigning this ring, you're also going to have proximity between the butyl proton and the hydrogen here, and between the butyl proton and the methyl proton and the hydrogen over here. So these are some highlights to look for. So any thoughts or questions on this little preview of a problem that focuses on Toxi and ROSI?
My one clarification was peak 24, you picked that out as an alpha, as the alpha proton?
Yeah.
Okay, just thank you.
So basically the region for amino acids and peptides, the region around 4 to 5 ppm is typically the alpha protons. 4-ish to 5 point something, 5.2, 5.3 is typically the alpha protons. I gave you a handout when we had that Toxi-ROSI lecture of all the amino acids, but of course it sort of makes sense. It's a tertiary proton, alpha to a carbonyl. So already we're sort of talking alpha to a carbonyl. If it were a methyl would be 2, but it's tertiary, so it's going to be closer to 3. And alpha to a heteroatom to a nitrogen. So now we're going to bring it, increment it downfield a couple of more ppm. And I'll tell you that being alpha to an amide, in other words, a hydrogen attached to a nitrogen, that's a hydrogen attached to a carbon that is next to an amide, is going to be way more downfield than a hydrogen that's attached to a carbon that's next to an amine. By the way, V, that is a very cute bird there. So a hydrogen that's on an amine, we're going to see a methyl group on an amine that's barely downfield of 3 parts per million. So that gives you an idea of sort of the baseline for a methyl group on an amine. A methyl group on an amide, which we have in this problem, instead of being barely downfield of 2 parts per million, just 2 and change, is going to be at 3 and change. So it's a whole ppm difference between a methylamine and a methylamide. But anyway, talking the alpha protons, yeah, generally about 4 point something to about 5 point something.
Got it. Thank you. Right. And I think, we also see that trend you were just referring to when we look at esters as well, right? That
yes, indeed. Not quite as pronounced, but yeah, methyl ester might be at methanol might be at 3.2 or 3.1 ppm. A methyl ester might be at about 3.7 ppm. So we get about an extra half a ppm for a methyl ester, and it's more like an extra ppm for a methylamide. All right, so that's problem number 1. Any other questions on this little brief overview of it? So I want to share problem number 2. So problem number 2 is a fun problem. It's an interesting ring system. And I was very, very proud of us maybe a little too proud of myself when we created created this problem, I thought it was a lot of fun, and I was walking around with a little gram bottle of this compound for making up the problem. So one of the issues that I like in problem number 2 is that problem number 2 sets us up very nicely for use of Hmbc in the way that we've talked about. And so I want to highlight the Hmbc spectrum. And I'm just going to label our resonances here. So we have 5A, 3B, 6C, 7D, and I'm going to show us some cross peaks off of them, 10C, 8F, 9G, and 11H. And you'll get that, of course, from the Hsqc, HMQC spectrum. So I urge you, when you're working with Hmbc, it's the technique to go to for putting the pieces together. And I say that it's very, very useful for carbonyls and for isolated methyls. And here, down at about 170 parts per million, we have 2 carbonyls. They're carbons 1 and carbon 2. And so you're probably going to want to pay attention to their cross peaks. And so, for example, we'll see that 2 crosses with 5A. I guess I generally like to write a little hyphen here when I'm doing this. So we'll see that 2 crosses with 5A, 2 crosses with 6C. And by the point you're getting to these 2 crosses with 7D, by the point you're getting to these, you're going to be trying to place these carbonyls in your molecule, and this will be very helpful. 1 crosses with 7D as well. 1 crosses with 10E. So what I'm doing sort of is breaking this problem down into a set of steps that we're going to do. Now, I mentioned isolated, let's see, what else did I mention here in terms of interesting features of the problem? So I mentioned here isolated methyl groups, and we've got an isolated methyl group here on the next page off of 12J, and I said that isolated methyl groups can be very, very useful to place. I said that we'll typically go ahead and cross out our vampire bites. I'm just going to number my carbons, and you'll see that right around 12J, we have our HMQC type of peaks here, our vampire bites, as I refer to them. And so I'll cross those out so I don't get distracted. And we see only 2 cross peaks off of this isolated methyl. 12J crosses with 9 and 12J crosses with 8. And if you have any doubt in your mind, you can look at these cross peaks. They're gigantic. These are some of the artifacts that come up from the processing of the spectra. If you have any ambiguity or any doubt about something like that, it's not an artifact, but I don't think it has anything to do with your molecule, and it clearly just is not even in the same class. So you can ignore that, and it becomes pretty obvious what you're looking for once you get in the habit of looking at these. So these are some of the highlights. The other thing I'd like to highlight in problem number 2 is how nice the 1D NOEs can be over here. And so you can see the 1D NOEs are pretty darn clear. When we irradiate, so here we're irradiating 11H, and we're seeing an NOE with 7D and an NOE with 8F and an NOE with N over here. And so that's very useful. You'll see other NOEs here. You'll just walk yourself through the interesting NOEs. Often we do sort of complementary experiments. So we saw 7D come up when we irradiated 11H. And so in a complementary experiment, we're irradiating 7D. It's not really a radiation because it's a gradient NOE experiment. And we see 11H come up. So that's nice and corroboratory. We also see 13M come up. And I like to urge people, when you're having trouble with assignments, don't sweat too much. So like here, you're going to see, all right, we can't really be sure if it's 14 and 15, if it's N or O coming up or what's coming up, or maybe we can, but you can just go ahead and deal with ambiguity or deal with duality of two things coming up by just labeling them together. So that's sort of a highlight of problem number 2 that I would like to share with you. So again, I'll take some questions on this. So one of the things I'd also urge you, so this is as you're getting around the stereochemistry, I'd also urge you to build molecular models. And a lot of the nice compounds that I give us involve bicyclics. I love bicyclic molecules because they have some nice conformations. I love cyclohexanes and cyclopentanes as well. I've given you a template to help with that, on that web page, although it's also possible just to start from scratch. We see bicyclo 113 systems, bicyclo 113 heptanes, bicyclo 221 heptanes. We see bicyclo 321 octane systems. You have a bunch there, but of course you can build your own. And in general, when you have a 6-membered ring in the molecule, it can sort of flip one way or flip the other. You may be in a situation where you are going to lock in and have a boat, and don't let that necessarily bend you out of shape if the steric interactions dictate that. So anyway, that's a little preview of problem number 2. Any other questions on it? All right, so this next problem I want to share with you is problem number 3. Problem number 3 was created by graduate student, also TA for this class, Sergey Levin. And this was, again, something that happened sort of as a byproduct of his research. Sergey was trying to do an Arndt-Eistert homologation on a CBZ derivative of glutamic acid. And he didn't get what he expected. And he characterized and figured out what he did get on this. And it's really a beautiful molecule. And I didn't think he'd be able to nail all of the diastereospecific assignments of diastereotopic methylene protons and figure out the stereochemistry of the molecule. But every stereocenter in the molecule you can figure out relative to each other. Every diastereotopic methylene you can figure out relative to each other. The NOEs really beautifully show the conformation of the ring in this molecule, as do the J values and coupling patterns. And so I want to show you some of the highlights of this lovely molecule. So in this molecule, I guess one of the things I'll highlight to you, and one of the problems we're going to have for solving the structure, is that we have an isolated methylene group. And actually, we have 2 isolated methylene groups in the molecule. And you've already seen we had a problem. We had that bromocamphor sulfonic acid problem in the last homework set. And we already saw how, although I say normally you want to focus on isolated methyl groups, in terms of placing them, isolated by Hmbc, isolated methyl groups can also be really, really interesting to look at. So I want to show you something that's really, really cool. Isolated methylene groups can be really interesting to look at. So this is the methylene group CHD HF, C7HDHF. And you'll quickly find it's a methylene group. You'll quickly see it's isolated. You can see this little bit of an AB pattern where the two peaks are tenting into each other. And if you look at all of your other couplings in the molecule, like even this ethyl acetate impurity, you very quickly can calibrate your eye on what a sort of typical J value is. So the triplet in the ethyl acetate is 7 Hertz. Here you see a little quartet in ethyl acetate here. So these are all J equals 7 Hertz. So it shouldn't surprise you for geminal coupling that for our J1 or our J2HH, it's going to be bigger than 7 Hertz. That's typical. We sort of see that, often 14 Hertz or thereabouts is a typical geminal coupling. Well, we've got another isolated methylene group here, and that's over here. And this one looks very, very different. C11HGHI. And so a couple of things that are sort of interesting about it. One is its chemical shift is sort of cool. It's, a 2.7, 3.0 ppm, and it's like, what is it doing there? The other thing is, look at the J2HH. Very, very different. Look at how small that is, particularly when it's compared to this other isolated methylene group. And so it's like, oh, that's really, really interesting. Why is this isolated methylene group so darn different than this other isolated methylene group? And so that's one of the things, that's several of the things you're going to be contemplating in this problem. Now, I don't know if you're going to go as far as Sergey did or as I did in handling this problem, but I look at the coupling patterns, and particularly when we come to the conformation of the ring, and it's just really cool and really beautiful what we see here. So, can anyone tell me what that coupling pattern is?
Is it a doublet of doublets?
It's a doublet of doublets. And what's happening with the heights of the lines?
Looks like it's probably tenting towards something else.
It's tenting towards something else, and you can kind of infer its coupling partner right over there. So I thought that's really cool. Look at this multiplet over here. This one's also sort of cool. Anyone know what that is?
A bad dream?
Bad dream, okay. We've seen something like this on the midterm, not exactly the same pattern, but kind of close in this idea on the center. So of this bad dream, how would we characterize it if we wanted to really go nuts and name it?
Is it two doublet of doublet leading into each other?
Well, it's integrating to one hydrogen.
Ah, okay, so is it quadruple? 4 Ds.
Yeah, D, 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 D. And so you can almost make out all the lines, 1, 2, 3, 4, 5, 6, 7 as this little shoulder, 8 and 9 are right on top of each other. And then we continue 10, and I won't bother to number on, right? It would, if there was no overlap, we'd see 16 discrete lines. But you can pick out, if you squint, you can pick out 15, and that center one overlaps and is doubled. DDDDs are a pain in the neck to analyze, but you probably can pull the J's out. And this pattern here is also really, really cute. Now, you might call it an apparent QD, and that wouldn't be completely wrong. But the thing that sort of impressed me about this is the heights are kind of 1 to 2 to 1. And so if you really want to analyze the hell out of it, you can analyze it as a doublet of triplet of doublets. If you're feeling really spunky on this, you can attack it. All right. So on this one, let's see. Again, we're going to have some carbonyls we're going to have to place here. So we have one carbonyl we're going to have to place here. And in our peaks here, we have 7D and 10E. And let's see. Whoops, I think I missed my numbering here. We have 7D and 10E and 7F and 11G. These are those doublets I was talking about, those isolated methylenes. 12H, we have 11I here. It kind of overlaps with 12J. We have 13K and 13L. And so I just want to take us through a few of the highlights here. We get a weak cross peak between the carbonyl and 7D. We get a strong cross peak between the carbonyl and 7F. So if you have any questions about that, you're still able to figure it out. If there's any questions about overlap here, you can look at the shape of your peaks and you'll notice how these look here. This is cross peaks of one with 12H and 12J. And we have one little more weak one with 13L. And remember, with the exception of isolated methyl groups, the absence of a cross peak or a weak cross peak doesn't mean it doesn't connect, because your J values depend on dihedral angle, particularly for your 3-bond J values. And as I said, we're going to struggle to place those isolated methylenes. And so you can see here that 7F is crossing with carbon number 9, right? This is 9. 10 and 11 are too close to call. We can do some pretty nice things by increasing our digital resolution in the F1 dimension. This one here, we go to, let's see, what do? We do F1 acquisition. We only did 256 points in the F1 dimension, so our digital resolution isn't that great. But even had we gone to 1024, 10 and 11 are just too close to call here. So we've got to deal with the ambiguity. 7F is going to cross with either 10 or 11, or potentially both, but we just can't tell which one it is. Anyway, so this is a start. This is a little bit of a preview on this problem. I guess I want to take you through one other thing here, and that is the nosy, which is really, really nice, particularly when we get to stereochemistry and conformational analysis. So here's 7D, here's 10E, here's 7F, here's 11G, here's 12H, here's 11I, here's 12J, here's 13K, here's 13L, and here's our C. I guess that was C over here in the nosy. 7D, 10E, 7F, 11G, 12H, 11I, 12J, and 13K, and 13L. And in this particular one, so the diagonal is negative, and in this one, we didn't plot it. Now James is probably going to plot our diagonals as dotted lines to show it's on the other side in the nosy. But here we simply left it blank. So our diagonal basically is here, and anything you're seeing is right on the diagonal. So you're going to start to pick out your cross peaks like 10E with 7D, 11G with C, 11G with 10E, 11I with 7F. And this, of course, will start to make sense to you. 12J with 7D. This will start to make sense to you as you've wrestled with these various cross peaks, 12J with 10E, so on and so forth. You can work on either side of the diagonal, or if you have any confusion, remember your best digital resolution is in the F2 dimension. And so if you have any confusion, like here, whether our cross peak is off 11I or not, you can look at the shape of that cross peak, and you can see pretty unambiguously it's 7D with 12J, not with 11I. That doesn't mean there may not be a cross peak to 11I, but clearly the width of this is very nicely showing that these cross peaks that I'm labeling here are with the 12J. But then you look at this one here and you see a very different shape. And so that's 7F with 11I. So you can start to pay attention to detail and really pick out these cross peaks. And if you work off of the NOEs, you're going to be able to get not only the stereochemistry of the molecule, but all of the diastereotopic methylene assignments. And if you pay attention to the NOEs and perhaps your J values, you'll even be able to really get the conformation of the ring in this molecule, which is very, very beautiful. And I urge you to make a model on this because it's an absolutely gorgeous molecule. So with that little preview, I'm going to stop the discussion of problem number 3. Any questions? All right, I want to talk about problem number 4 at this point. So problem number 4, so in about 2011, we introduced Hsqc toxi into the class. And I wanted to go ahead, remember we talked in the last lecture about Hmqc toxi and Hsqc toxi, which are comparable techniques that differ just slightly in pulse sequence. And so I wanted to deal with a problem that had severe overlap. I love really pretty spectra where you can see all your resonances, and we often select for them in the course, but sometimes nature isn't so kind, and no matter what you do, whether you switch from chloroform to benzene or not, your resonances are going to overlap and you'll have a mess. And that's what I wanted to create in this problem here. And the other thing I really like is the fact that most of the time you don't simply get an unknown bottle of an unknown material and be told figure out the structure. You have a very specific problem. Often that problem involves stereochemistry, and sometimes it involves conformational analysis. So this particular problem I set up as, let's figure out what diastereomer we have. And so we have a molecule, and I gave 2 stereocenters that were undetermined. And then we have the possibility of 4 diastereomers. And the molecule involves one of my favorites, a Trans-Declin system. And so normally we think of the Trans-Declin system as being like this, where you have a ring system like this. We have some models on the page. And you have your very nice canonical cyclohexane rings. And you're going to build some models, and you're going to figure out, because your substituents can go here and they can go here, and you're going to figure out that tetrahydrofuran and its stereochemistry. I'll give you one cautionary note that if we have our oxygen over here and our carbon over here, we can't span that ring. And so in the cautionary note, you're going to build models. You're going to build pi-mole models for all possible diastereomers. In that particular case, you're going to have to accept that ring has no choice, that ring of the decalin has no choice but to go to a boat conformation. And that's the only way you can span it. So you're going to have to also build a boat there and make a model with a boat, where now you can go ahead and you can actually span for your furan structure. All right, so that sets the stage on the conformational analysis. And then I want to move on in to highlight the Hsqc toxi, because that's going to reinforce the lecture. All right, so one of the nice things we see in this molecule is we've got 3 distinct spin systems. So remember, the spin systems are the isolated groups of spins. So we have one spin system here. We have one spin system here. Of course, the methyl groups are their own spin systems, but they're kind of trivial. And finally, one spin system here. So essentially associated with each ring. One of these spin systems involves 3 methylene groups. One of these spin systems involves 2 methylene groups and a methine. Another of the spin systems, the third spin system, also involves 2 methylene groups and a methine, but you'll notice one of the methylene groups is alpha to an oxygen, so it's really going to stand out. And what I want to show you for starters is how powerful the Hsqc toxi can be for seeing your spin systems. Now, on this one, we really went to town with our number of increments in the F1 dimension. So if you look here, we went ahead in the acquisition parameters and did 1024 increments to get as good a digital resolution as we could. And that's going to allow even carbons that are really close together, like these 2 carbons, that'll allow you to resolve them. So I'm going to give you some highlights here. So number 2 is a methylene. Number 3 is a methine. Number 4 is a methine. Number 5 is a methylene. Number 6 is a methylene. And you're getting that from the depth. 7 is a methylene. This is all sort of the low-level analysis. 8 is a quat. You can tell that even without the depth. 9 is a methyl. 10 is a quat. Then we come on to 11 is a methylene. 12 and 13 are both methyls. 14 is a methylene. And 15 is a methylene. And 16 is a methyl. And you'll get all of that easily from the depth. And, you know, I said that we set up this problem deliberately to have a mess. And we have a mess here. We've got a lot of overlapping resonances. But what's nice is the Hsqc toxy really allows you to pick out the spin systems very, very easily. And with this particular Hsqc toxy, I give you a variety of mixing times. So in this particular Hsqc toxy, we have a long mixing time, and we can walk our way through each spin system. Or to put it another way, each spin system pops right up. And so you look at this here, you look at this track over here in the Hsqc toxy, and immediately it tells you one of your spin systems, C11, H2, C3H, and C2H2. In other words, it's a spin system that encompasses one methine and two methylene groups. And I'll point out that the methine and methylene group are reasonably far downfield in the NMR spectrum, and you'll be able to figure out more about which ring these correspond to. And you can see a very different track under this peak here. And so this track is another spin system. So this one encompasses C14H2, C6H2, and C4H. And so this is another spin system in the molecule, and immediately you can pull that spin system out. The last one's a little tougher due to overlap, but you start to see this nagging pattern come up again and again and again. And you start to realize, oh, wait, here's our last spin system. It's so it's C15H2, C7H2, and C5H2. In other words, that's that ring that has 4 methylenes to it. And what I think really shines with the Hsqc toxy is you can use different lengths of mixing time to sort of walk your way through almost like a cozy. So I'll show you the 20 millisecond mixing time, and you can see that we've gone from C2H2 and C11H2 is just starting to has come up. If you look at a shorter mixing time, I think I give you 5 and 10 as well. You'll see that at this point, C3 is just starting to come up, and you'll be able to walk your way through this spin system. Whoops, that's C3H. And you'll be able to do the same thing over here where we've gone from C6H2 and C14H2 is coming up. And in the next one, which I won't show you, by the time we're up to 50 milliseconds, I think 50 is the next one I give you, C4H will come up. So you'll be able to not only go ahead and pick out your spin systems, but you'll be able to walk your way through the spin systems. The very final thing I want to show you for this problem is the Hmbc, and I urge you to use your isolated methyls. So we have C12H3, I think it's H. We have C9H3J. We have C13H3K. And we have C16H3L. And you're going to be able to walk through and identify all of the cross peaks. And look how nice it is with 1024 scans in the 1024 increments in the F1 dimension. So they're really, really sharp. You'll be able to see all the cross peaks like C6H2A or H2, C3H, and C1 off of this methyl group, and ditto for this track and this track and this track, and that'll allow you to assign your methyls and then figure out the stereochemistry right off of them. So this is going to be a very, very nice example of this sort of problem. And then you're going to turn to your nosy spectrum, and you're going to start to figure out your various cross peaks, 2A and B with, I'll say, cross 11E. Here's a teeny tiny cross peak, barely perceptible for 2A with 12H. One of the things that is bad that we don't give you the spectra themselves because it would just be too much work for you. But what would be really nice is you could go a little bit deeper and say, wait a second, is this really a cross peak? I'm going to go a little bit deeper and see if it really is above the noise. We probably should have gone a shot deeper. And you'll notice here, remember I said James will plot the diagonals with a dotted line to indicate the phase. So here's our diagonal, and you can see our little dotted lines indicate negative phase. All right, so that's a little preview of problem number 4, and I'll take some questions over here at this point on this. All right, and I want to take about 2 minutes to give a quick preview of problem number 5. So problem number 5 is another problem where I tried to create severe overlap, and I want to show you a few highlights of it. So this is a structure determination, but you're also going to have a stereochemical determination. So you'll notice we see a familiar pattern here in the H1 NMR at about 6.5 to 6.8. Oops. ppm, so you'll have a familiar pattern as a highlight. I deliberately chose a molecule that's going to give you some severe overlap. And so the Hsqc toxy is going to help you out. Like many natural products, this molecule has some isolated methyls. We know what to do with isolated methyls at this point. And again, I'm going to just bring our attention to the Hsqc toxy spectrum and show how you can basically pick out these toxy tracks that show you your spin system. So you can immediately pick out a spin system. Here, you can pick out another spin system over here. You can see this pattern again. This is again with a longish mixing time. So you'll be able to pick out your spin systems and maybe even walk your way through them. Last thing I think I want to show you on this particular problem is we did one thing bad in this. So here's the Hmbc. We didn't perfectly line things up, so this may confuse you. We have just a slight error. So here are our isolated methyls, and when we referenced it, there's ever so slightly a shift here, so don't sweat about that. Just recognize that, yeah, we didn't line things up to the nearest hundredth of a ppm, and just cope with it, that they're just a hair off of your peak here. So we could have gone back and done that. And again, you'll be able to very nicely pick out your cross peaks off those isolated methyls to assign them in the Hmbc. And I think here's the nosy, and I don't really have anything special to say about that, except that'll be useful for figuring out your stereochemistry and conformation of the molecule. So that's a highlight of the 5 problems that you're going to have for this weekend. Any final questions on the 5th problem? All right, as promised, what I'm going to do is treat this like a slide deck. And so I will email it to you. So if you didn't take notes or your notes are too hasty, you'll have this. And of course, some of this, like on this video, are going to make more sense once you've attempted the problems. So feel free to pop up the video if you want when you're working the problems, to use it as sort of guidance on these exercises. I've even seen people on the final exam, when we've done it in person, go back to the class videos on various topics and watch them while they're working the final exam. So that's even an option. All right, I will have my office hours today at the usual time at 5 o'clock. So if anyone wants to stop by and discuss the problems or anything else, I'll have my office open. And I think after about 7 o'clock, I'll just leave the channel open if people are still there and want to use it as a problem session together for cooperative learning. All right, have a good rest of your day. And if I don't see you, I will see you. If I don't see you this evening, I will see you on Monday. And so have a good weekend. Take care.